Okay, we're going to start talking about a pendulum now. So if we have some support that allows us to swing a mass on a string. So we're going to have a couple parameters. We're going to have the mass of the object and the length of the string. We're also going to measure its position based on its angle from the vertical. So that'll be our angle right there. Okay. And we're going to try and see what kind of motion would come out of Newton's second law on this force. The forces, we'll find out what the forces are and then see what kind of acceleration it has. And from that, try and get a position as a function of time. Okay, so in doing so, let's look at our free body diagram. So over here is the mass. It's got a tension pulling up on the string, and it's got force of gravity pulling down. Okay. Well, the string by virtue, or sorry, the mass by virtue of the string is restricted to move in a circle, and so it'd probably be best to choose a coordinate system that is radially inward and tangential, which the tension is already radial inward, so we can break our force of gravity into two pieces. Okay, so we'd have FGR, the radial part, and then FGT, the tangential part. Okay. Now you can see that the mass is not moving in and radially in or out, and so the tension minus FGR must equal 0. There's no acceleration, therefore there's no net force, therefore those two must equal 0. But we don't actually really care about that for this type of motion. What we're trying to find is the motion that causes it to accelerate. So that's going to be this force right here. Okay, so if we take a look at that, and in terms of the angle theta, it's not too hard to show that this is the same angle theta. Okay, the string makes that angle theta from the downward direction, and FG is downward, and FGR is to the is radially outward, same direction as the string. So that means that we have FGT equals F net T equals MAT, which we know for circular motion equals VT squared over R, and R in this case is L. Okay. Now, FGT is going to be mg sine of theta, because I could put it right here, and that is opposite the angle theta. All right. Now I'm going to go ahead and write this as MAT. We actually don't need to go as far as the circular motion step for this. But we need to do a couple things here. Okay, we're going to use our fact that this is going to go over an arc. Okay, there's an arc there, and we can call that of length S. And there's a relationship between S and theta, and that's by the radius. And so S is equal to R theta. In this case, that's L theta. And which means that theta is equal to S over L. Okay? Now, that's helpful, but I don't want to really put that into here right now. Not quite yet. We need to do what's called a small angle approximation. So if we assume that theta is sufficiently small, now we'll figure out experimentally what sufficiently small means. But if we assume it's sufficiently small, there is an identity that says that when sine of theta, or sine of theta for theta really goes to 0, when theta is small, sine of theta is close to theta. It can be replaced by theta, which makes sense because sine of theta approaches 0 as theta approaches 0. And so they actually can get very close to being the same value. Okay, so with that being in mind, we can use this to say this is approximately equal to mg theta. And I'll just finish that over there. And using our identity from the angular length to the arc length, you can say that's S over L equals MAT. Now I'm going to do something here that is a little bit of a calculus thing. So MAT, that's the same thing as MDS squared, or d squared S dt squared. It's the second derivative of the arc length, or in other words, velocity is the rate of change of the arc length. Acceleration is the rate of change of the velocity, so that means acceleration is the second rate of change of arc length. Okay, so now that we've got that, well, I can do a couple things. Let's go ahead and cross out our mass, and I have an equation here that says S, oops, let me change that back. I have S G over L equals d squared S dt squared. Okay. Now, I can stop there, but for calculus reasons, we can go ahead and say, okay, I am looking for something, a function of S. So I'm trying to find a function of S, or a function S of t, such that when I take its second derivative, I get the same function back with a g over L. Okay. Now we can learn in our different ways of integration that one way to do this is just to make a guess. Make a guess of a function that will do that. And so we need a function that when you take its derivative, you get the same thing back. And I just realized I made a minus sign mistake. Okay. Since theta is measured from the vertical, S needs to be measured outward positive, which means this force is always negative coming. So S would be positive to the away from this downward part. Okay, so we need to have a minus sign there, 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 and there. Okay, so I apologize for that mistake. But so now basically I need to get the same thing back with a minus sign and a g over L when I take the second derivative. So something that I know is that a sine or cosine do that. So if I just make an assumption that S of t equals some amplitude cosine of some omega t plus phi 0, just like we have before. If we assume our standard simple harmonic oscillator function, then if I take the first derivative, I'm going to get the v of t, and that the derivative of cosine is negative sine, and then doing chain rule, acting on the time inside, pulls out this other omega there. So I get a negative omega a sine of omega t plus phi 0. And then take the derivative of that, is going to give me a of t. And the derivative of sine is positive cosine, so I have minus a cosine of omega t plus phi 0. But again, I have to do the chain rule, or I guess on this step, I have to do the chain rule there and give me another omega. So now I have two omegas, or omega squared. Okay. So this equation is now the same thing as S of t, except I have a negative omega. I haven't. So as long as I have an omega squared that equals something out front, then I'm done. And we can compare that to this and see that omega is going to equal the square root of g over L. And so we've just found that this pendulum motion is also oscillatory and simple harmonic, with the angular frequency being square root of g over L. So it doesn't depend on mass at all. It does depend on the inverse square root of L and g.